Welcome everyone back to Chapter 4. This time we're in Section 4, the chain rule. In order to inspire kind of why we want this chain rule thing, I want to imagine really quick if we wanted to take the derivative of this function right here, this 2 plus 3x, all of it being raised to the 16th power. And so if I was thinking right now, if I needed to take the derivative of this, kind of the only thing we have is that we could represent this 2 plus 3x raised to the 16th as 2 plus 3x times 2 plus 3x times 2 plus 3x over and over and over 16 times, right? 16 of these being multiplied by each other. And I guess I could technically use a product rule, right? But we saw last time in the product rule section that even when you have three things being multiplied by each other and you want to apply the product rule, it's a big pain, right? So 16 things being multiplied together, this is going to take forever. I mean, if this showed up on an exam and you decided to use the product rule way for 16 things here, that would take all 50 minutes and then some. It would take forever. So there must be a better way. And the answer is yes, there is. And of course, it's called the chain rule. So the way the chain rule works is that it recognizes, I guess, this function right here as a composition of functions, right? So it's one function, 2 plus 3x, being put inside of another function. That is, stuff's being raised to the 16th power. So if we remember back to our good old algebra days, we may have come across compositions of functions. So now we're going to learn how to take the derivative of compositions of functions. All right, so let's stare at our theorem here, the chain rule. So if f and g are both differentiable functions, that means that it makes sense to take the derivatives of these things. Then the composite function, right, f composed with g, or f of g of x, is differentiable. So again, it makes sense to take the derivative of it. So what is the derivative? Well, here we go. The derivative of h, aka the derivative of a composition of two functions, is going to be equal to, you take the derivative of the outside function, so f, leave the inside function alone, and then you multiply by the derivative of the inside function. And that right there is the chain rule. Now, actually, this looks pretty darn slick when you use the Leibniz denotation, right? So remember, we brought this up here in 3.6, the Leibniz denotation. And so if we set g of x equal to u, if we just use this little placeholder variable here, u is g of x, then we can formulate this as, remember, here's the Leibniz notation. This is saying the derivative of h with respect to x. This would be equal to the derivative of h with respect to u times the derivative of u with respect to x. And this is one of the beautiful things about the Leibniz notation, is that the Leibniz notation, remember, it looks just like fractions. These really aren't fractions, but because it looks like fractions, you can see maybe these du's would cancel out, and what you would have left is the dh and the dx, right? So dh dx, it makes a lot of sense. All right. So let's see how we can actually use this, right? This is kind of confusing. Let's use it for a real-world example here, or for a real-world problem. Use the chain rule to calculate out this derivative here. So this is a composition of functions. One function, 2 plus 3x, is being put inside of another function. That is, stuff's being raised to the 16th power. And so let me start off. I'm going to try using this Leibniz notation at first, because I think it makes a lot more sense. So let's try this. So let's see. First of all, we need u to be equal to g of x. Remember, g of x is the inside function right here. So if I'm looking at this and I'm trying to figure out what is u, what is my g of x, what is the inside function, hopefully after staring at this for a minute, we can agree that 2 plus 3x is the inside function. And so if I was to replace this 2 plus 3x with a u, right, I would get u to the 16th power. And so this is the thing that I want to take a derivative of, and now you can see it has u's. So this is really an h function. So if I want, I can do h equals u to the 16th, right? And so according to this, if I want the derivative of this function with respect to x, well, I can take the derivative of h with respect to u, right? Here's my h and it has u's in it now, and then multiply that by the derivative of u with respect to x. So let's try it out. So if I want derivative of h with respect to u, so u is my independent variable here. Well, this is just going to be the power rule, right? That means the 16 is going to come down, and then I'm going to have u raised to the 15th power. That's not so bad. Okay, how about this other one? I need a du dx. So that's a derivative of u with respect to x. So here's my u function. I need to take the derivative of this with respect to x. So du dx. Well, this is just a linear function, so right, the derivative is going to be the slope. That's going to be 3. Okay, so according to this, if I want dh dx, or h prime of x, I'm going to do dh dx. This is going to be equal to these things multiplied together. So 16 u to the 15th times 3. And now since u was something that I constructed, right, we should trade back in. Everywhere you see a u, you should trade back in, in terms of x's. So everywhere I see a u, I'm going to put in this 2 plus 3x. Let me do that, and let me also simplify, right? So 3 times 16 is going to be 48. Everywhere I see a u, I'm going to go ahead and write 2 plus 3x. And that right there is my final answer. That is how I would take the derivative. And it's a little bit confusing at first. I get that. But the claim is that it is way, way, way faster and better and just all around excellent, much faster than if you were to do the product rule up here. Right? So you definitely want to do this method, the chain rule, if you come across an example like this. Okay. Let's go ahead and try another one here. Calculate the derivative of a of t. And I have the square root of 1 minus 1 over t. So again, let me go ahead and try to use this method that I had back here. So that is, I'm going to try to figure out what is my inside function, right? I'm going to define something to be u at first. What is my inside function? So my inside function, right, I have a square root. That seems to be the outside function. So the inside function is going to be whatever's on the inside. So I'm going to do 1 minus 1 over t. Okay. And so I already have a, right, and I'm trying to find the derivative of a with respect to t. And so according to the chain rule, this would be the derivative of a with respect to u times the derivative of u with respect to t. And again, you kind of think out these du's would cancel, and that would just give you the dA dt. So first of all, it's pretty easy. I could take the derivative of u with respect to t. Let's do that one really fast. Derivative of u with respect to t. Well, the derivative of 1, that's a constant. That's just going to be 0. And then remember, 1 over t, that's the same thing as t to the negative first power, right? So if I want to kind of pull off to the side here, and I want to take the derivative of 1 over t prime, I'm going to remember that this is the same thing as t to the negative first power. So if I take the derivative of that, the negative 1 would come down, and I'd have t raised to the negative 2 using the power rule. Okay. But now remember, I don't want just the derivative of 1 over t. There's this little minus sign. So again, the derivative of 1 is 0, and then the derivative of this with the minus sign, so I have an extra negative, right? That constant, that negative 1 really follows us along. This is going to be equal to positive, right? The negative of a negative is positive t to the negative 2 power. Okay. And now let's write, everywhere I see this 1 minus 1 over t here, I'm going to put in a u. So this is going to be a is equal to the square root of u. Work on my handwriting there. Now I can take the derivative of a with respect to u. Because again, remember, this is just the same thing as u to the 1/2 power, right? The square root is the same thing as being raised to the 1/2 power. So if I want the derivative of a with respect to u, the 1/2 is going to come down. Then I'm going to have u to the negative 1/2 power. Okay, so here we are. The derivative of a with respect to u, that's going to be 1/2 u to the negative 1/2 power times the derivative of u with respect to t, that's going to be t to the negative 2. And then finally, remember that everywhere I see a u, I'm going to go ahead and plug back in this 1 minus 1 over t. So 1/2 1 minus 1 over t raised to the negative 1/2 times t to the negative 2. And there we are. That is my final answer. Okay, the claim is you're going to get so fast at these, you're going to be doing a lot of them, that we're actually going to be able to do these quite quickly rather than breaking it all down. But I thought it's useful, especially the first time you're seeing this, to really break it down and do it slowly, really think about what is this outside function, what is this inside function, and using this Leibniz denotation here. Let's try one a little bit faster though, right? So suppose a particle's height is given by h of t is equal to this function here, this t over t plus 3 all being squared. T is the number of minutes after it is released. how fast is the height changing? Right? How fast is the height changing? This is a rate of change, instantaneous rate of change, right? So you're thinking already derivative, even though it doesn't say take the derivative. So how fast is the height changing 1 hour after it's released? Now this is a little bit tricky here, right? Because t is supposed to be the number of minutes, right? So 1 hour, this is going to be the same thing as 60 minutes. So all of this information combined, these words are telling me that I want to find out h prime, so the derivative of h, this is telling me how fast it's changing, at a specific time, right? And that specific time is 60 minutes. So my goal is to find h prime of 60. So notice when I take the derivative here, well, we're going to have to use the chain rule, right? Because there's one function, this t over t plus 3, inside of another function. It's being squared. So let's go ahead and try taking the derivative of this. And now I'm going to do this the faster way. And of course, we'll explain this more in class, but here we go. So the outside function, right? If I just think about the outside function here for a second, I'm going to cross this out even. Think about the outside function is that stuff's being raised to the second power. So if I took the derivative of the outside, right, that would be the 2 would come down, and then all that stuff would be raised to the first power, right? Leave the inside alone. So whatever's on the inside, now I have to look back at it. So what's in the inside, that's going to be t over t plus 3, and then multiply by the derivative of the inside. Ooh, and this is where it's getting more complicated, right? Because now when I multiply by the derivative of the inside has a quotient rule going on. So let's go ahead. This is a combo problem. It's a chain rule and a quotient rule. So let's go ahead, take the derivative of this. So the derivative of the inside here, this t over t plus 3, quotient rule. Take the derivative of the top times the bottom minus the top times the derivative of the bottom, the derivative of t plus 3, that has slope 1, all divided by the bottom squared, t plus 3 quantity squared. And there we are. Now we can go ahead and simplify this. So 2, of course, when things get raised to the first power, that's just itself here. And then let's see, distribute the 1, really that doesn't do anything. And so I have t plus 3 minus another t. So that's just going to be a 3, right? Because the plus t and the minus t cancel out. And then t plus 3 quantity squared. And so if I wanted to, right, I know how to multiply fractions together. We have a 2 and a 3 and a t all in the numerators. So that's going to be 6t. And then in the denominators, this is going to be a t plus 3 and then 2 more t plus 3's. So this is going to be 3 t plus 3's. Since they're being multiplied together, I'm going to write t plus 3 quantity cubed. And there we are. And so I want not h prime of t so much, right? I want h prime of 60. So everywhere I see a t, I'm going to go ahead and plug in a 60. So this is going to be h prime of 60 is equal to 6 times 60 divided by, let's see, 63 cubed. What a nasty number. Let me pull out my calculator really quick. So 6 times 60 divided by 63 cubed. And just thinking about 63 cubes a lot bigger than this up here, so I know it's going to be a number pretty close to 0. 0.001439. So I'm going to do 0.00144. So 0.00144. And now remember, whenever you have a derivative here, whenever you have a real world problem, we need to think back to units. So the height here is feet, and the time units is minutes. So therefore the derivative is going to have units of feet per minute. Right? So that's how fast the height is changing 1 hour after it's released. It's barely changing at all, but it's changing at 0.00144 feet per minute. So it's important to include our units here. Remember, the units of the derivative are the same as the units of the average rate of change, right? The derivatives of h divided by the units of t. Yeah, units of h divided by the units of t. All right. So you can see we're going to get pretty fast at these things. Let's do one more here, a more real-world example. 4.5, the percentage, y, of a total personal consumption, so how much your total spending is, of an individual spends on food is approximately y equals 35x to the negative 0.25 percentage points. Interesting. All right. So the percentage of total personal consumption an individual spends on food is around this. Okay. Where x is the percentage an individual spends on education. Okay, so it depends. I guess probably the more you spend on education, probably the less you spend on food. We could go ahead and graph this here. And let's see. So let's suppose in this case, an individual finds that she is spending x equals 7 plus 0.2t percent on her personal consumption on education, where t is the time in months that's January 1st. Estimate how fast the percentage she spends on food is changing on November 1st. Be sure to specify units. So how much you're spending on education depends on time, and then however much you're spending on education, that influences the percent that you're spending on food. Okay, so this is a more real-world example, how compositions can come up. And so we want to know let's see, November 1st, I want to know, estimate how fast the percent she spends on food is changing. So let's see, percent she spends on food, that's our y value. Y value is changing on November 1st. So this is talking about a derivative of y with respect to time, right? So how fast is it changing on November 1st? Be sure to specify units. November 1st, okay. So this is at a very specific time. Not just the derivative function, but we want at a very specific time, right? So, okay, we want at November 1st. So let's think about this. T is the number of months after January 1st. So if I did t equals 0, that would be 0 months after January 1st. So this would be January 1st. If I did t equals 1, that would probably be February 1st. If I did t equals 2, that would be March 1st. And I don't know about you, but when I think January, I think the first month, right? And when I think February, I think the second month. When I think March, I think the third month. So we have to be careful, right? So November 1st, when I think of that as the 11th month, you can see that the t value is actually one smaller than that, right? So this is when t equals 10. So when t equals 10, that's going to correspond to November 1st. So if I wanted to use the Leibniz notation, it'd be the derivative of y with respect to t when t is equal to 10. All right, so this is the quantity that I want to find out. And we can see that this depends on x here. So I'm going to go ahead and use my Leibniz notation to do the chain rule here, because this is already kind of broken out. So I'm going to do the derivative of y with respect to t is equal to the derivative of y with respect to x, since I already have an x right here, times the derivative of x with respect to t. So now again, you can imagine these kind of x's would cancel out in some sense, and you'd have dy dt. Okay, so the derivative of y with respect to x, I can do that. So let's see, this constant 35 is along for the ride. And then this is going to be a power rule, right? So this negative 0.25 comes down, and then I get x raised to the, and I have to subtract 1. So this is going to be negative 1.25 times the derivative of x with respect to t. So the derivative of x with respect to t. So here's my x function. It has t's in it. I can take the derivative with respect to t. In fact, this is linear, so I know that the derivative is just going to be 0.2. Okay. Now, just as before, right, I want to plug in a t, I guess I want to plug in a 10 everywhere I see a t, but I don't see any t's here, right? So I want to go ahead and substitute everywhere I see an x, I'm going to put this stuff up here. I'm going to put the 7 plus 0.2t. So let's see, I'm going to rewrite this one more time. dy dt is equal to, all right, let's go ahead and pull out my calculator and simplify this down a little bit, right, because we have a 35 here. We have a negative 0.25, and we have a 0.2. All of these are being multiplied by each other. So negative 1.75. And the only thing that I haven't taken into consideration is this x raised to the negative 1.25. And so again, everywhere I see an x, I'm going to plug in. Oops, I forgot my negative sign, didn't I? Negative 1.75. Yes. That's going to change things. Negative 1.75. And again, everywhere I see an x, I'm going to go ahead and plug in 7 plus 0.2t. Okay, now I'm ready. Now I can actually plug in my 10 everywhere I see a t. So the derivative of y with respect to t, evaluated when t is equal to 10, is equal to, all right, now I need my calculator again. Oops, wrong one here. So I have my negative 1.75, and then I need to multiply this by 7 plus 0.2 times t. And my t is 10. Raised to the, and I'm going to do parentheses just to be careful, negative 1.25. So negative 0.11226. I'm going to do negative 0.1123. Negative 0.1123. So that's how much it's changing, right? It's decreasing, it looks like. As she spends more on education, she spends less on food, right? And it seems like November, right, this is an increasing function, so she's spending more and more and more. So yes, it should be decreasing. That makes a lot of sense. Notice right here it says be sure to specify units, right? So the units of y, this is the percentage of total consumption. So this is going to be percentage, let's see, of total consumption. Divided by the units of t, right? So t had units months, right? So the percentage of total consumption, I guess maybe I should specify even more. She spends on food. Spent on food. Is decreasing each month. Not by a whole lot, right? But it is decreasing. It's getting smaller. That's a negative number. So there we go. All right. So that's how we can see a chain rule problem in kind of a more real-world situation. That's it for the video. I'll see you guys in class.